Hello, everyone. In this episode, we'll cover how to solve ordinary differential equations using Runge-Kutta method. So, a brief introduction. So, commonly occurring is solving ordinary differential equation, which is a form of there's a y and it changes. So, let's say for a time, dy dt equals to a function which is a function of y itself and time. And how do we solve it is commonly occurring. And a common thinking would be that, okay, so we can just look at the changes in y. So the yn plus 1 step minus yn, which you can put it on this side, then equals to this f at the yn and tn times h, which is the time size. So something like this. They're putting the dt on this side and hope that it works. Sometimes it does, but it turns out that the numerical errors can accumulate rather fast and makes it very inaccurate. So people usually try to find other ways of doing it. And a very common thing is an algorithm called Runge-Kutta fourth order method. And it basically breaks this delta H step into 3-4 different pieces, in this case, 4 pieces. How we do it is that, well, the yn plus 1 step, so 1 delta time steps ahead is yn plus, and then it's 1/6 of k1 to k2 to k3, k4, and then the delta time step, where k1 is evaluating this at yn, and then k2 is moving it at half time step, and here half k1 step, k3 is another half step, and then half step of k2, and then finally tn plus h and yn h, and then k3 step, and then plugging these in here. How it works, I encourage you to just search the web and you quickly find that how we do it. It's a very common method, and we'll show how this is implemented. And here's, in this program, I'll just show you a common example of the epidemic dynamics. During the COVID, we have seen a lot of research popping out, showing how this susceptible population and infected population and recovered population work out. Basically, the susceptible who may get disease meet with the infected people and scale with the population. And with certain rate, the susceptible population decreases and become infected population. The infected population basically increases, they get this, but also a fraction of it, like fraction gamma, will become, that leaves this population, this infected population, and become recovered population. Well, it's a very simple common model that has been around for a long time to describe how sick people, infected people, and how they recover and how the dynamic works out. And typically the susceptible population decreases and the recovered population will increase over time, and the infected people may reach a peak and then die out here. So let's see how this gets worked out. Okay, so here is the program that I already uploaded from Google Drive. So here is my Google Colab notebook. You can upload it again. If you have a file, you can upload and then you can get there. But go to this program. I basically need not much, just to plot for matplotlib and some random numbers and NumPy. Let's load the library and basically show you how this epidemic dynamic equation, which is integrating the S and I and R over time. And we have to know how the derivatives work out, the time derivatives, which are here. So beta times S times I divided by N, and that positive sign minus gamma I, and gamma I here. A common form is though that people sometimes think instead of big S, the small s being the population and small I being population infected and small r being the population R. People work with this equation instead, but we'll just work with this here. Okay, so the T is current time and Y is the vector. So S and I, so the big S, big I, big R, we'll just put them in a vector so Y0 is S, Y1 is I, and Y2 is R. And we need some arguments, the beta and the gamma and the population. So we'll pass this. So this shows how to program that. So first, we define the ODE system, the equation that you want to solve. So, and in terms of derivatives, basically you give the T and Y and the argument being the beta, gamma, and N. That's that. And the dy0, dy1, dy2 is the changes in S, changes in I, changes in R. Then minus argument 0 is beta, so that's the beta, y0, which is S, y1, which is I, divided by argument 2, which is population. And the plus sign comes here, minus argument 1, which is the gamma, times y1, which is the infected. And then lastly, the recovered derivative, the change is the argument 1, which is gamma, and y1, which is I. Then you put them all these changes in an array. So it's the dy comes out in a vector of 3 numbers, the changes in S, I, and R. All right, so let's do that. Now here's the Runge-Kutta fourth order routine. So we define a function here. So you can just pass the function, the ordinary system equation here, ODE, you can pass that, and then the time and Y and time step and argument. So here the function is passed, and then the function requires, so in our case, T and Y and argument. So T and Y and argument at TK, and then half step plus, and then the function evaluated here. So that would be our K1 and argument, K2, K3, and K4 here, isn't it? F3 and times dt, and then the arguments. Okay. And then return the average of these. Remember the 1/6 of the time step of F1, F2 twice, F3 twice, and then F4 will be returned. So that is one time step of using the Runge-Kutta method, just like we saw in the PowerPoint slide. Okay. So now we can actually use this, our function we want to solve. And this is a generic function of just time integration of one step. Then here, so the time step being 0.01, so we run from 1 to 100. Then the arguments being beta of 0.5, gamma, the recovery rate of 1/3, and then the population of 1,000. The y0 is we start with out of the 1,000, we subtract 10 and have the infected population being 10. So we have something to start with, and the recovered population is 0. So we accumulate the state history and initialize the yk being y0. So we start with yk and time step 0 times 0. So we accumulate, append all the YKs that we each time step increase. And look here how simple it is. The ODE system, which we defined here to get dy, isn't it? Every time we can evaluate it. So we pass that function here to Runge-Kutta, and then the t, yk, dt argument will solve one time step and get our yk, which is cumulated. And we do this over all the time variables here. Right? So we can do this, and it will compute all the 100 time steps. Then we can print it and then plot the time history of a susceptible, infected, recovered population. Well, you got the picture that we saw. So this is a simple way, I guess, The one that I want to emphasize is that how to do a time integration of system of linear ordinary differential equations. Yeah. You can, of course, pass the arguments which are time dependent, and then you just have to redefine here. So this was how to solve ordinary differential equation using the Runge-Kutta fourth order method. Thank you for watching this video.